Okay. So we're looking at this example before we went off. Let's continue from here. So we are asked to find, he says the number of cars that arrive at a car park follows a Poisson distribution with an average of 10 cars per hour. Okay. So we're given a constant rate of 10 cars per hour. Okay, so that is a homogeneous, okay, Poisson process. Then it says find the probability that exactly 30 cars, okay, will arrive. So our X or our K, okay, is equals to 30 cars will arrive between 10 to 12 p.m. Now 10 to 12 p.m. is a 2-hour time step, okay? So from 10, 11, and then we have what? 12, okay? This is 2 hours. So it means that your T is equals to what? Is equals to 2, okay? So, and we're asked to find the probability, okay, of observing X being equal to what? 30. Okay, 30 cars. So per our distribution, that will give us lambda T, okay. Then we have raised to the power X e raised to the power negative lambda T, okay, over X, okay, and that should be lambda T will be 10 times 2 e raised to the power 10 times 2, okay, over our X is what? Our X is 30 factorial. Okay, so kindly find that for me. Do the calculation for me. Yeah, so what are we getting? What are we getting for our answer? Adai, what are you getting? So far, it's only Gilbert who has participated in class today.
Sir, 3.77
3 points.
times 10 with 77.
Okay. So, I hope you raise this to the power 30. That is X, okay? So don't forget that we left it out. So that is 20 raised to the power 30 times e raised to the power negative 20 over 30 factorial. So if you didn't do it that way, redo it again and let me have your answer. Yeah, so what are we getting for the answer? What did we get for our answer?
The 3.77 times 10 raised the power negative 33.
Okay, 3.77 times 10 raised to the power negative 33. Any other answer? So that is going to be quite small per the answer we are seeing over there. That is very, very small. The probability is very small, okay, to observe such an occurrence. Okay, and of course, like we saw earlier, the mean, which is the expectation, is also lambda. Okay, the mean of the process is equal to lambda. Okay, so that will be 10 cars per hour.
Please, you've muted yourself.
Okay, sorry. So I was explaining that to get the mean and the standard deviation, you first need to check the time, the given time interval here. Here is from 9 to 1. So you have 4 time intervals. So your standard deviation is the square root of lambda t. Okay, because we have t involved here for a homogeneous Poisson process. So that will be the square root of 10 times 4. Okay, which will be the square root of 40. Square root of 40 should give us, square root of 40 should be what are we getting for the square root of 40? You can just type it for me. Send me a chat.
That's 6.32.
So we have 6.32. Okay. So that will be the standard deviation, okay, for the number of cars that will arrive at the park. Okay, now moving on. So we've covered a number of distributions. We've looked at the Bernoulli, we've looked at binomial, we've looked at geometric, we've looked at Poisson. Well, I think we'll also look at the exponential. Then what I'll do is I told you last week that I was supposed to group you. This topic, you usually do presentations, but I think it's going to be difficult on the online program. So what the assignment I'm going to give to you after today will be for you to also go and write up on the hypergeometric function, okay, the hypergeometric function, and the negative binomial function. So you, just like I explained to you, give me the context when it is used, then you give the probability distribution, the expectation, the variance, and then cite an example, okay, on how it is used with the solution. Okay, so for two distributions, that's hypergeometric, and for negative binomial. Okay, that is an assignment for you. I'll add it to your next assignment anyway. So start doing it before I post the assignment. Now, okay, so let's look at the last distribution. I've just remembered we didn't discuss assignment 1, so we'll have to look at it today. Okay, yeah, so let's move on. We have the next distribution is the exponential process. Exponential process is used for, distribution is used to model time, okay, time between Poisson processes. So example, you've arrived at a bank. What is going to be the time you spend in the bank before you accept? Okay, so this is used in a number of processes like waiting time, okay, length of phone calls, waiting time in the queue, any type of queue at all. So it says that the exponential distribution describes the times between events in the Poisson process in which events occur continuously and independent at a constant average rate, okay? And once you identify the context of the process, then the parameter is also 1 over lambda. So the density function is what you have here, which is lambda e raised to the power negative lambda x, or if you want to use a parameter that is going to be 1 over mu, then in this case, this is also going to be what? 1 over mu. So you're going to have x, negative x over mu, okay? So if you are to plot the probability distribution for an exponential process, you are going to make use of this, or you make use of this function. Okay, then let's see if there is any example on this one before we move on to the assignment from last week. Today our network is not too good, but we are managing. Okay, so CDF is also provided here, okay? The CDF is 1 minus the exponential of negative x, okay? Either use times the lambda or over mu, okay? So that will give you the cumulative distribution function. The variance of the process is 1 over lambda squared, and the expectation of the process is 1 over lambda. So when given a question, you make use of these functions, okay? You make use of this to find the probability of the process. Then you make use of these two for the expectation and the variance respectively. Okay. Yeah, so moving on. I think there should be an example on that. Yeah, so we are told that we have assume the length of phone call in minutes is an exponential random variable x with a rate of what? Lambda equals to 1 over 10. Okay. If somebody arrives at a phone booth just before you arrive, find the probability that you have to wait, you will have to wait less than what? 5 minutes. Less than 5 minutes means from 0 minutes to, just before 5 minutes, you understand? Which is a CDF. So if you're going to calculate a CDF, you know what to do, okay? The CDF function is given here. Is 1 minus e raised to the power negative lambda x, okay? So we make use of that to find the CDF. Okay, so you have here, your rate has been given, the rate was given in the question to be 1 over 10, okay? The rate was given as 1 over 10, okay? And then your x is 5, okay, less than 5. So it's just 1 minus e raised to the power what? Negative lambda x, okay? So you apply that. Once you do the calculation, you should get 0.3935, okay? That is the step. So 1 minus e raised to the power negative lambda. Like we said, lambda is 1 over 10. So you just put it here, times your x, which is 5. That will give us the probability. Then if you want the probability greater than 10, greater than 10 can easily be found as 1 minus the probability of x less than what? Less than or equal to what? 10, okay? So you take note of that. So which means you find that probability. And then if you want the expected value, okay, we saw earlier that the expectation of the process is what? 1 over your mu, 1 over mu or 1 over lambda, okay? And then your variance is what? 1 over lambda squared, okay? Good. So you can equally find that too with the given values. Let's see if you have we have the answers here. Okay, so that's the answer for the second one, which is being estimated in the video over here, okay? So if you want the probability greater than, that is 1 minus the probability less than. So you estimate 1 minus e raised to the power negative 1. And that will obviously give us e raised to the power minus 1. So on that note, I will wrap up with my presentation on the various statistical models which can be employed in modeling different scenarios. And if you were in class early enough, you would have seen that article where I employed, you can see I employed the cumulative distribution function for the geometric. I also employed components of the Poisson, and I employed the Markov chain as well, okay, to come up with that first model and the simulations. Okay, if there is any question relating to anything that we've done or in relation to the assignment I've asked you to go do, you can ask whilst I also search for your assignment and bring it up.
Sir, please, can you post the assignment in the group first?
That's which one? Which one? Is it the new one or the old one?
Today's one. The new one is different.
Okay. Okay, I'll do that. Okay. I'll send it to you. But I'll include it in your, that will be your assignment, either assignment 4 or assignment 5 on Limas. So in any way, you still see it on Limas. Okay. So if anybody has, Gilbert, you have the assignment question I gave you the last time. Assignment 1. If anybody has it, you can just read it. Let's address it. Solomon, the slides, you have them already. Yeah, and one thing about on the Limas, okay? The slides I'm using are the same slides on Limas. It comes with PDF and PowerPoint. You understand? So everything has already been summarized. The only difference is probably during my presentation, I may add one or two examples, okay, to make things clearer. But it's basically the same slide I'm using from Limas. And if you check, we are on module 2 of the Limas slides, okay? Okay, somebody also says, sir, we don't have the slides. So it's the same thing I'm saying. Unless you want to tell me you've not checked your slides from Limas, or if there is an issue. Gilbert, have you checked from Limas whether the materials are there? I wasn't recording. So we are supposed to generate simulation trials, okay? And once we've obtained our simulation data or trials, we need to compare with observations from real world, okay? So we'll use observations, okay, from real world data. So we observe what is going on in real world. If we are simulating the number of cars that will arrive at a traffic light, then we need to go and observe, okay, the number of cars that happen at that traffic light within that time period, okay, and compare with our simulation what? Our simulation output, okay? So, and that process is what we refer to as what? Validation of the data, okay? So in ensuring accuracy, one step is to conduct validation, okay? Validation, which means comparing simulation data with what? With real world data to ensure that they are similar, okay? Then another way of ensuring it, like I said, as for the choice of the base model, there is nothing you can do about it, okay? But the selection of your parameters, relevant components to the system model is also very important in predicting the outcome of your simulation work. Okay, the simulations you obtain. Okay, good. So if you leave out key parameters of the process, of the real life process, then you end up running simulations which will be far from, they will be far from what? The observed data. So these are two sources of ensuring that, okay, we have an accurate system. Okay, then finally, I ask you to distinguish between analytic solution and numerical solution. And a lot of you just copied my solutions, my notes back for me. Okay, of course, we know analytic solution is manual. Numerical solution is for more complex systems, which means that we need a computer, okay, a computer program or computer aided solution.